Hello everyone, welcome to eMemory's webinar today. Today we'll be discussing about the design in advanced node based on eMemory's latest breakthrough on N4P and the ongoing development. And today I'm so glad to have Joy Lee back with us. Hi Joy.
Hello everyone, my name is Joy and I'm eMemory's marketing manager.
And also we have extra guest for the first time today, Howard Tan from PUFsecurity.
Yeah, I'm Howard. I'm in charge of technical marketing in PUFsecurity and very happy to see everyone here.
Within the past decade, we have witnessed a significant technology leap. Nowadays, you probably cannot go a day without hearing something about autonomous driving, AI, 5G, or something related. And heavily relying on the computational power, the IC behind this application actually all depend on the advanced process technology. But just advanced technology alone won't make this happen. This IC happen, right? I mean, we need a lot of other IP. So I think this is why we bring both of you to here today that to talk about some of this. Because with the latest development from eMemory, I understand that eMemory has made some breakthrough development on N4P. Joy, could you give us some insight about this?
Our NeoFuse OTP and the PUF-based solution has been available on many FinFET platforms. According to our internal statistics, we have already more than 70 tape-outs move into production below 16 nanometer nodes. And recently, as you mentioned, we just qualified our OTP and the PUF solution on TSMC's N4P, and we expect that the qualification of our OTP and the PUF will be complete on TSMC's N5A in the next month. And in addition, we are currently developing OTP and the PUF on N3E and N3P to meet more demands from the mobile and HPC sectors. And as for N3A, we also once the platform is ready, we will soon put our OTP and PUF into development, and we will continually to provide our OTP and PUF solutions to meet our customers' demands.
Thanks, Joy. So Joy, you just mentioned about fulfilling customers' need in advanced node, which I want to go a little bit deeper. So Howard, I would want to direct the next question to you is, so what kind of trend, what kind of market trend you observe here? Because otherwise, why would an IP company continue to invest into developing such advanced node technology IP?
Yeah, upon the lot of project in advanced node in our hand, because of SoC getting complicated because due to multi-core architecture, and also this will come to different requirements, no matter in dynamic storage or static storage. And the other part, the customer type quite different, so their resource management also different. All this part will lead our IP development goes different way. So this is our experience so far. Yeah.
Thanks. I will come back with you for more detail on this one. But before that, I want to come back to the NeoFuse detail first. Joy, could you give us some detail on NeoFuse's feature and benefit on how it makes NeoFuse so special in advanced technology?
Okay, maybe we can start from our IP key features. Our NeoFuse IP on N4P contains an OTP array up to 4K 40 bits, along with a maximum 8 kilobits PUF array, and it features a 1-bit programming scheme, which helps a lot in terms of reducing power consumption and the size of the charge pump. Other key specs can be referred to the table shown here. And for security applications, we have customized IP with an additional small information block for customer use, and with features like power floating detection, data fault detection, metal shielding, etc., to protect the data from side channel or invasive attacks. As for N5A, the qualification spec is actually very similar to N4P, but we did further design efforts like for redundancies, agent simulation, and spare I/O for ECCs. And we also did qualification items under more strict conditions, like higher stress voltages and under higher temperatures. And of course, the total design and qualification rule is complied to TSMC's design for manufacturing rules.
So I understand that it's never easy to develop an IP in advanced technology. So could you take the audience deeper to share what makes NeoFuse successful in the advanced node?
Okay. An important feature of our NeoFuse IP is our proprietary in-cell voltage divider. And this design helps a lot to improve OTP performance. We know that to apply a high voltage to program the NeoFuse cell will bring some issues like ghetto current or leakage from punch-through effects. And therefore, the programming should be controlled in a precise manner. And our countermeasure is to add an internal voltage divider to mitigate the high voltage across the transistors, and to reduce the ghetto current and punch-through effects, and therefore makes our IP more robust and reliable. So I would say that this unique feature helps a lot to us to verify and qualify our OTP in new platforms with less troubleshooting efforts and less debugging efforts, and also brings great satisfaction from our customers. So it is really important to choose a good memory cell architecture when it comes to embedded memory IP.
Hey, thanks, Joey. That's interesting. But can you elaborate on why this in-cell voltage divider was added? Because wouldn't we suffer some trade-off as well? I think the audience will be interested to know about.
Well, the truth is that we get more benefit from this. While the individual cell size grows slightly, the structure greatly simplifies the overall macro, which includes other peripherals. All of these combined have proved to be very valuable as we move into the advanced process.
So, Joey, if I understand this correct, you're saying that when we look at OTP, we need to look at from the macro point of view, meaning that the entire IP.
For OTP memory, while the cell behavior is the most essential foundation, we must consider the entire macro as a whole to achieve the optimal design. If the memory cell has a small sensing window or is easily disturbed, the IP then needs additional designs to the program and read circuits that increases the total IP size, and sometimes even requires an additional mask to the manufacturing process to solve some problems. Our in-cell voltage divider optimizes the cell performance, so we can minimize the peripheral circuits and achieve a smaller overall IP size, especially on the FinFET platforms, and doesn't need any additional masks. The exceptional cell performance also makes our development into advanced process much easier, as our IP has worked on the first car for a long history, and so is our recent N4P qualification. All of these contribute to our design wins in 7 nanometer and below, and some projects have already gone into production. My understanding is that our OTP is the only technology that has gone into mass production in 7 nanometer and below. With such a strong track record, NeoFuse continues to propel our customers' success.
Joey, thanks for the explanation. So, NeoFuse has been around the market for quite some time, coming from legacy node all the way down to the advanced process technology. I mean, we talked about 16 nanometer before, and in the last couple of years, we talked about N7 and 6. Now we are on to N4 and 5 platforms, and even going further to the 3 nanometer, right? So I imagine the team must run into some certain difficulty. Could you please share some of the experience with the audience?
Okay, based on our experiences in advanced nodes, most of the challenges comes from the peripheral circuits. Compared to 7 or 6 nanometers, OTP on 5 and 4 nanometer platforms have to operate under lower voltages. The operating voltage of the NV devices lowered from 1.8 to 1.2 volts. And that means our charge pump circuits have to endure similar operating voltage levels with a single gate oxide. So that brings some difficulties to our peripheral circuit designs. So although the single gate oxide brings some trouble to us, but actually our engineers soon overcome these issues because we have a relatively stable and robust memory cell. So since we don't have to manipulate the programming scheme or adjust any process steps, we can still have a more compact peripheral compared to other OTP technologies.
Thanks, Joy, for your explanation. And Howard, what Joy just talked about, actually there's a point I want to bring up and ask you a question about it. The fact that going from 7 and 6 nanometer technology down to 5 and 4 nanometer technology with the operation voltage drop from 1.8 to 1.2. While we pose challenge to NeoFuse development and they overcome, I'm wondering, wouldn't that pose similar challenge to other technology like eFuse? What's your take or your opinion or what you have heard from the market?
Yes, actually the challenge will happen in the in-field programming. So SoC design getting bigger and complicated. So the whole project development will need many times for designer to program eFuse by different purpose in the whole development period. So that will cause two problems. One, if you need to design the eFuse in in-field programming, you will need additional extra voltage, which is 1.4 different to your core logic power supply. And the second, you will need additional pad with ESD device. So all this kind of design will lead different cost and complicate. So the problem is when the eFuse user are going to the advanced node, they will feel the flexibility will not so easy to use in advanced node SoC.
Thanks, Howard. So far, we have discussed more on the IP's individual features and the specs. I want to switch the gear a little bit toward the IP's application now. Howard, can you share your insight from the SoC design perspective on why NeoFuse is, being so optimal for the advanced node technology?
Talking about the advantage and the application, I think we can put more focus on the SRAM issue in high performance computing. In the market side, the emerging application such as the electrical vehicle and voice recognition, large learning model, they all require SoC and multi-core to handle the massive data. In the meantime, SoC also need huge SRAM to achieve the performance to deal with the faster computing and the large learning model. In the meantime, we also receive more and more customer requests from the market in the past year because of SRAM issue. They are working on the AI or HPC, even the ADAS SoC. Okay, obviously we found the market trend and the customer needs, they echo each other. So we try to find out what background story inside. Okay, it's very simple. First, SoC also need advanced node to achieve the target of computing power. Second, SoC designer usually or must will need huge SRAM, which may fulfill by different discrete SRAM module. And third, because of huge SRAM density, they will need professional DFT tool to complete the SRAM repair process. The function of OTP is used to store the address of the MBSR tool, which is a kind of general solution for SRAM repair. So we found the whole story why the market trend and the customer demand come to us.
Thanks, Howard. You just mentioned about SRAM repair. Could you care to give it a little further elaboration on the SRAM repair part, and also why should people choose eMemory's OTP solution to do this function?
Sure. Upon the last question, we just know the SRAM repair basically means to replace the bad memory bits with redundancy bits. In past, SoC designer or DFT testing engineer, they use eFuse to use for the storage to save the redundancy bits. We know the eFuse IP is the default offer from foundry. However, it will come a very critical issue when the SRAM density goes up. Okay, so I prepared 2 slides to explain why this come to a very critical issue and how our solution can deal with the critical issue.
Right.
For example, if SoC require 64K bit of storage for SRAM repair, the IP size of 64K bit eFuse will be very big, which leads higher cost. But if designer consider to use smaller eFuse to save IP size, which will face yield loss issue and will be very critical in advanced node because the huge wafer price. Now, in our project, our real project, if the designer use our IP solution instead of eFuse, for example, 64K bit OTP only takes 11% area compared with eFuse. That means SoC designer can fully fulfill the SRAM repair requirement and no need to face the dilemma between IP size and the yield loss. So our solution can be regarded as a better storage for the SRAM repair, no matter for the cost and the device performance.
So obviously, area is not the only concern as Howard just mentioned. So Joy, since you just talked about cell structure, let's come back to eFuse a little bit. Is there other concern eFuse will pose in doing SRAM repair from your opinion?
If you accept the IP size is larger in high density, it also known for reliability problems like growth back issue. A programmed eFuse cell has some chance to go back to the connected states after many times of reading. On the other hand, NeoFuse doesn't have this kind of problem. It has much better reliabilities.
Thank you both. The explanation about how NeoFuse could be a great solution for SRAM repair. But every time when we talk about a change of IP, I think that brings a nightmare to the designer, right? They will think about what kind of risk they're gonna face, what kind of effort they're gonna face. But I think risk-wise, given NeoFuse's strong history in the past decade, I think we can throw that aside for now, being in mass production for so long. But what about effort-wise? Previously, the tool would take eFuse as a default function to do the SRAM repair. But what happened if they want to make the switch to use, let's say, the NeoFuse to do SRAM repair? What kind of effort the engineer will be facing?
Yeah, I'm so glad you asked this problem about the effort, additional effort. Actually, our IP almost no additional effort to migrate to our IP from the eFuse because our IP solution already integrate all the necessary controllers and interface. We can take a look to our page about the IP architecture. Okay, you can find There's actually a high integration IP which include not only the OTP hard micro cell, but also all the necessary controlling logic RTL, such as memory partition and the regulation of the whole test methodology, and also the each kind of behavior model. Furthermore, you will find all the interface already ready, like APB interface and the auto load for preload data. Of course, we have ready the interface for the MBSR tool. So let's take a look for the next page. We are take more about the interface. We already have integrated the APB interface to connect the main system and the subsystem. We provide TDR to help designer to implement debug functions. We also provide the auto load, which is kind of a wire bus, which can preload the OTP dedicated address data to clock trimming or voltage trimming application. Of course, we also integrate the most important, the interface for MBSR, especially for SRAM repair. The total design just for the one purpose, designer can just drop to use. I think all the designer can feel very, very convenient to merge our IP into their SoC.
Thanks, Howard.
Yeah.
So before we end today's webinar, I want to roll back a little bit. Earlier, you mentioned that you have received quite a lot of requests in the past year. What's the project status now? How are they doing? I think that the audience will be quite curious about this.
Yes, indeed. We already have more and more customers come to us, and more real projects ongoing. Some of them already going to tape out. No matter US, China, Japan, all the key customers, or no matter it's big design house or small startup, they all come to us because of this kind of application. And furthermore, we are so happy. They appreciate you have seen the total integration, because the design already saved their resource and they can just make the project on time to finish. And we are so proud we can make it and really help customers to enhance their project performance and the tempo. Yes.
Thanks, Howard. And before we end the webinar today, I want to remind every audience that our Q&A session are still open. You can submit your question in the Q&A box below. And thank you both for bringing such great insight to share with everyone today. So, Joy.
Okay, thank you, everyone. I'm looking forward to share more story with you next time.
Thank you, Joy. And Howard, would you like to say something?
Yeah, thank you for your time to see our video. And SRAM repair is just one of advantage for our IP solution. And we also have a lot of purpose from customers like security, like PUF, like other application. So I'm looking forward to have more chance to share our progress and development to all of you. Thank you.
Thank you again for your attention. We look forward to seeing you again soon next time. Bye-bye.